reactions. Okay, the things you always need to know is actually your delta G, right? So how do you know your delta G? There are a few ways you can actually check out the delta G. Okay, so the first method, if you go to page number 4, okay, the first method you can actually calculate your delta G naught is use the table. Okay, so you have reactant, you have products, then you can calculate the delta G naught for your system is going to equals to the G naught formation of your product minus the G naught formation of your reactant. Okay, so if today you encounter one equation that you can actually find all the formation gives free energy of each species, then you can just calculate all of them. Okay, and then calculate all the GF for your product minus all the GF for your reactant. Then you can get the delta G for that specific equation. Okay, but this will only happen when your reaction is actually happen under standard condition. Okay, if today your reaction is actually happening not under a standard condition, then you cannot do it this way. Okay, so there's a second method that you can actually use to calculate your delta G naught for your system. Okay, so the general idea is actually you get the delta G naught of your solution from delta G naught of your gas. Okay, because you know once the reaction is complete, if you have a solution, then you have corresponding vapor pressures. And we know how to calculate delta G naught for the vapor phase. Okay, then you can start it from there and go back to here. Okay, give you one example. Assuming that they have CO2 solution. Okay, and once you reach equilibrium, we always say, okay, at equilibrium, the mu G is going to be equals to mu liquid. Okay? And we know how to write the mu G, right? Mu G is equals to mu G naught plus RT natural log, assuming it's ideal gas, then that's your mu G. Okay? So the mu L is going to equals to your mu L naught plus RT natural log A. Okay? So how to express the A here is actually the key. Okay? We know CO2 dissolves slightly into the water. Okay? This is water solution of aqueous. Okay? And the solubility is related to your Henry's law constant. Okay? So you can write the A is going to be equals to the vapor pressure you can measure above the water solution and reference that to your Henry's law constant. Okay, and this will be your activity. Okay, then we're going to put this in here. So you're going to have this will be P over KH. Okay, so since these two is going to be equals to each other, then you know your mu L is going to be equals to mu G naught. So you move this term over here, you minus that, so the P and P cancel out. So you're going to have plus RT natural log KH over P naught. Okay, And P naught is equals to 1. So this is going to equals to mu G naught plus RT natural log KH. What this means is actually if you know what is your mu G naught for the gas, okay, basically for your CO2, if you know the solubility of your CO2 inside the solution, you can calculate the chemical potential of CO2 for your system. Okay? They say, assuming today you have 1 atm CO2, okay, and it's K, okay, and the concentration of CO2, the concentration of CO2 in your solution is equals to 3.4 times 10 to the negative 2, okay. And then if you know the chemical potential of CO2 under standard condition, is equals to negative 395 kilojoule per mole. Assuming you get these informations, okay, then you can calculate the chemical potentials of CO2 in the solution, okay? Because mu L is going to equals to mu G naught plus RT natural log KH. Okay? So the mu G naught is negative 395. R is 8.314. Temperature, let's say room temperature is 298. Natural log KH. So we need to know the KH, right? So here we need to use the Henry's law. Okay. The solubility is 3.4. It's 1 atm, so let's P.